So last chapter, it's going to take us some time to go through this chapter 8. It's about the memory system. In here, we're looking at the memory system performance analysis. We're going to spend quite some time in the cache design. There are 3 different techniques that we're going to go over. If you have a time, we're going to get into virtual memory. Definitely we are not going to get into these 2. So in the major components on computer, in chapter 6, we look at the data path. In chapter 7 and also data path. In chapter 8, we'll look at the memory. In the memory, we have a main memory, cache, and the secondary memory. We'll just focus on cache in this chapter. Computer performance, it really depends on cycle time. So when we get something from the main memory, it's going to take quite some time. So that's why when we say in the pipelining, LDR and STR is the longest time we need to have. Therefore, when we use single cycle data path, we have to use LDR as our standard cycle time. You have to use it. So it's typically far away from the processor. That's why we want to have some cache in between. And the memory system, when we design the workstation, typically we spend 25% of the cost for the processor and then 25% of the cost for the memory. So the memory portion is one of the major. And the rest, 50%, is a power supply box, all those gadgets. 2007, this micro SD card is 128 megabyte. 2017, 128 gigabyte. Okay. So right now I check it September when I update all of this. There's a 1 terabyte, it's about $90. And I look at the last year, we had a 2 terabyte, about it was $50. So the memory price is jump up quite well. It's in the trend in the future, especially for AI era. Memory area is going to be a hot topic because we need to have a high performance chips and a lot of data we need to store. Right now all this generative AI is in the cloud, but Apple, Samsung or Google, they try to have this AI capable chip into their own device, into here, not going through cloud, so that we can have a faster interaction with the AI. If that is the case, this memory chip price is going to go up, and designing memory chip is really on demand. It's a good future in there. They cannot be replaced by AI. And memory systems challenge, make a memory system appear fast as possible and close to the processor. And we need to use the memory hierarchy. I'll show you that later. Ideal memory, this is our goal as a computer engineer, electrical engineer. Our goal is to reach this. Fast memory, but it's cheap and unlimited access. That's our goal. This is the memory hierarchy. So the process is up here, close to me. I have a cache, and also cache, we have a level 1, level 2, and then main memory. And after main memory, we can connect to secondary memory, like a flash drive or external drive. And also, in the back end, we can connect to the virtual memory. This is the price per gigabyte. And then access time, as you can see, virtual memory access time is huge. Cache is much faster. And the bandwidth. We'll talk more about the bandwidth a little bit later. Let's talk about SRAM versus DRAM. SRAM is faster, but it's really expensive. And SRAM is much smaller. But DRAM is slow, huge, and cheap. That's why our main memory, typically DRAM, cache is majorly SRAM. When we talk about pipelining, when we have write back stage writing into ID, but in the ID stage, one of the source register is the same as the destination register in the write back stage. We said there's no hazard. Why? Because we're going to write first and then read. In the typical clock cycle is single data rate this way. So anytime we go up, we're going to write or read. Only thing we can do is the positive clock edge cycle, whenever clock goes up, we take the one action. However, in that pipelining, we can write before we can read within the single cycle of the clock. So that's what we call double data rate. And nowadays, we do quad data rate. So we're going to read 4 times. There are 2 clocks. Fit into the process, we're going to have 4 reading and writing, or 4 actions can be done within the clock period. So that's the quad rate machines. And DRAM performance, row buffer allow several words to be read in the parallel way. Synchronous DRAM, we can improve the bandwidth, and then there's a banking allows simultaneous access to the multiple DRAMs. This is what we have in our textbook, and I got this information from Hennessy book. This is one word wide, everything is one word. This is one word main memory, one word cache. Okay, so if this is the case, we want to calculate the bandwidth. We can also do wider memory. So in this case, 64, 2 of this memory width, 64. Of course, we're going to have the bus, and then we can increase the cache as well. So that's wider memory organization. And then interleave the memory organization. That's what we meant by banking. So when we look at all of these examples, and we're going to calculate the bandwidth, some assumptions: 1 memory bus clock cycle for address transfer, 15 memory bus clock cycle required for DRAM access, 1 memory bus cycle for word process. And then we'll look at these 4 different scenarios. First one, and there are 2 different scenarios for the case, and then the case number 3. The first, so we have a processor on the top. There is a buffer or bus. It's connected to all of this cache. Now, this is 32, 32, 32, 32. Okay. And then we have a bus. Bus size is going to be 32-bit because of the memory size is 32-bit wide. If this is the case, this guy, memory 1 bus clock cycle for address transfer, going from here to here. So basically, I want to access to this guy. So we're going to look at the 4 different scenarios. Regardless of those scenarios, the miss penalty is going to be only 1. Why? Because from the process, I'm going to send my address to the cache. If I got it, I got it. If I don't get it, we need to go down. So I need to send my address only 1 time. That's the 1 memory clock cycle penalty. The next one, DRAM access. Since we have 32-bit and 4 times of 32-bit, we have to access it here, 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 and here. Okay? So we need to go through the cache first before we getting into main memory. Therefore, we need to have a 4 times of 15 clock cycle as a penalty. And then when you get the hit going from here to here, that's going to happen only once. That's why it's 1. So when you add them up, that's the total 65 per cycle. And the bandwidth, we can calculate. Total width is a 16 byte, 4 byte, 4 byte, 4 byte, 4 byte, 16 byte over total 65 cycle. So this is 0.25 byte per cycle as a bandwidth. And then second, we're going to have a wider one. If we have a 4-word block and 2-word wide, we cannot have 3. So under this scenario, either we have a 2 or 4, because it always works 2 to the power of something, right? So when we have a 2-word block, same assumption. If this is the case, we have a 2 times 15 and 2 times 1, 33 bus cycle. So the bandwidth is 0.48. When we compare from the previous, it's not quite double, but it's close to the double, but it's not quite double. And when we have a 4-word, something like this, then we have a 1, 1, 1 penalty, 16. So this is the kind of optimal scenario. We have a 0.94 byte per cycle, the bandwidth. When you say bandwidth, talking from cache to memory, that's the bandwidth. So this is the wider bandwidth. The last case if we have something like this, now the memory, we need to put that as a bank, 32, 32, 32, 32. Therefore, this is the same, but going from here to here, we know which bank, so we need to have additional 1, so that's the 0.8 byte. In these days, HBM system, this is really buzzword these days because we are using this HBM for AI machines. So we have NVIDIA, leader of AI chip, followed by SK Hynix, HYNIX, as Korean company, and then Samsung is the third one. So those are the three main companies. There are HBM 1, 2, 3. Right now we are in the HBM 4 stage. This high bandwidth is the emerging type of computer memory for the high bandwidth and lower power assumption. Those are the key words they're trying to develop for this type of memory. And then we're going to use SD-RAM in here and synchronous dynamic random access. And it is used to AI chips, provide massive data throughput required for the training and large AI model. So now you may wonder, what's the major difference between high bandwidth versus wide bandwidth? The best way we can put that in is wide bandwidth. You can think about 6-lane highway. There are 6 different cars that can go through that highway, right? So we have 6 different tasks we can do really fast. That's the wider bandwidth. However, high bandwidth, we're talking about the throughput. So it's a wide water pipe. When you guys were in the circuit, I always use the water pipe, compared to the current. So in this case, the water pipe is the task that we're going to go through, finish. So larger water pipe, we can get more water through the system, right? So we can easily finish the work with the high band as well. So that's the major difference between the high bandwidth, wider bandwidth. Locality. So we have the temporal locality, spatial locality. You can take a look at it, but anybody been in the library, look for our textbook, computer architecture related textbook, circuit related textbook, systems and signal control, maybe not. Do you know where they are in our library? Which floor? 4th floor. There's all engineering textbook there. That's a spatial locality. I want to get some engineering book. I want to go to 4th floor. In that area, there's every engineering books there. That's the spatial locality. Now, I'm working on, let's say, research paper on this computer architecture. So I need to get some computer architecture textbook from there, right? So obviously I want to go 4th floor because I know information is 4th floor, spatial locality. When I need some information, I just read from, in front of the shelf and put it back. That's stupid. I may need it again. Therefore, typically what we do, I'm going to take those 2-3 books and sit it in the table because I know I may need to access the same book again. So that's the locality in time. If the data used recently, most likely we're going to use that data again. If the data used recently, okay, and some other data that I need in the future, it's going to be nearby. So that's the temporal locality and spatial locality. Hit rate. I want to access to upper level memory, could be cache, level 1, level 2, whatever that is. I need block X. So I'm here, I'm the processor, I'm here. I'm going to go one lower than me. Hey, there is information I have. So that's a hit. This time I need the block Y. So I'm here, I'm getting into here. I cannot find the block Y. If that is the case, I need to go one lower. That's the miss. Hit time is the time to access the level of the memory hierarchy. And miss penalty is the time to replace the block. Block Y is the one that I need. I just go down there and get it and just leave it there. That's dumb. Since I need this guy, most likely I need this guy again in the near future. Therefore, I'm going to bring this guy and store it in here. Therefore, to calculate the miss penalty, time to replace the block in the upper level plus time to deliver the block to the process. That's the miss penalty. So typical miss rate, we're going to calculate number of hits divided by number of memory access, which is the same as 1 minus miss rate. Here's the miss rate calculation. And book also talk about average memory access time. It's the average time for process to access data. This is the formula. Program has 200 load and store instructions and 1,250 of these data values in the cache. That means the hit rate is going to be 1250 because 1250 is in the cache out of 2,000. That's the hit rate. And miss rate, 1 minus of this guy, therefore is a 0.375. Here's the second example to calculate average memory access time, AMAT. It's the time for getting into time cache, which is 1 cycle. The miss rate for the cache, which is TMM, that's the same miss rate for the time, 100 cycle. And the miss rate is the 0.375. You multiply with it, and then AMAT, okay, it's going to be 38.5 cycles. Okay, so Amdahl's law. This is the how we calculate the speed up. This person, Amdahl, developed this Amdahl's law as calculating the speed up. Speed up is defined by execution time for the task without enhancement over execution time for the task with the enhancement. Obviously, execution time without enhancement is larger than execution time with enhancement. So this speed up has to be greater than 1. If you say speed up is less than 1, let's say 0.9 speed up, it's not speed up. It's really lagging the performance. So speed up has to be greater than 1. Take a note on that. And also we can say the performance with the enhancement over performance without enhancement. So in the Amdahl's law, it said if enhancement accelerates a fraction of the task, so the fraction of the task, we're going to call it as an F, and then by a factor S much, how much we can make it faster, some portion of improvement, then what we need to do execution time with the enhancement is going to be 1 minus F, that fraction, plus F over S, the factor, time execution time without enhancement. Now the speed up is defined as without enhancement over with enhancement. So if we move this guy, we divide both sides by execution time without enhancement, then execution time with enhancement over execution time without enhancement is this guy, right? But that's not speed up, that's 1 over speed up. Therefore, the speed up is going to be 1 over this fraction. So we'll come back to that. And then one more equation I want you to write down. Execution time after improvement equals execution time affected by improvement over amount of improvement plus execution time unaffected. Some portion of the computer is not going to be affected by any improvement. That execution time, we need to keep it there. Okay. Only some portion of the improvement, we need to use that formula. Yeah? Yes. This plus this. Okay? So let's do first example. Enhancement runs 10 times faster than original, but it is only 40% of the time of that enhancement. Overall speed up. So based on this formula, we can get speed up equals to 1 over 1 minus F plus F over S. What is F in this case? 0.4, 40% as a fraction. So F value is going to be 0.4. And the factor 10 times, that's the S. So when you plug those numbers in, so 1 minus 0.4 plus 0.4 over 10 and 1.56, that's the overall speed up. So this time it's a little bit more complicated. We can improve CPU, and CPU is only used 50% of the time. And we can make it faster by 5 times faster without affecting I/O performance. And then it costs 4 times. CPU is used in 50% of the time. Input-output portion is used for 50% of the time. And CPU is 1/3 of the total cost of the computer. The question is this increasing CPU speed by 5 is a good investment when you look at the cost versus performance viewpoint? That's the question. So let's find out speed up first. So 1 minus f. F is what? 0.5. And s is going to be what? 5. So 1 minus 0.5 plus 0.5 over 5. We have 1.67 as a speed up. And then now we need to calculate the new machine's cost. Here's how I set up the equation. 1/3 is the CPU improvement, but we're going to improve the CPU. What's the cost? 4 times of the cost. If we actually improve the CPU only, we need to multiply 1/3 of the parts times 4, and the rest is what? 2/3? 2/3 of the rest of the parts, cost is going to be 1, still be there. That's how I calculate that. That'll give us 6 over 3, and which is 2.0. When you compare this and this, speed up we reached 1.67, but cost is 2.0. I mean, I would say this is not a really good investment, right? Cost is more than the improvement, the speed up. So you need to mark it 1/3 is coming from CPU total cost, and that's the 4 times the original right now. Right now is 1. However, we need to pay 4 times of the current cost to improve this guy, plus the rest of the parts, 2/3 times 1, because we are not going to spend any money on that. So it's 1. So it's a 2.0 versus 1.67. Hey, Dr. Kim, it's just for 0.33 difference, but that's huge. It's not worth it. Okay, let's move on. Caches. So this is the main one. I'm going to spend quite some time in here. Highest level in memory hierarchy right next to processor. It's going to be fast because it's right next to me. I can always access to the cache. Typically 1 cycle or less. Ideally supplies most of the data to processor. Usually hold the most recently access to the data. So when we do the cache design, these are the 3 questions that we need to ask ourselves. What data is held in the cache? How is the data found? And what data is replaced? So I'm going to go down there, main memory, bring it to the cache, because within the cache, the information that I want right now is not available. First question is, how do I know the information that I need right now is not in the cache? That's the first question. And the second question is, how I go down main memory, find whatever I need, bring it to cache. But we said cache is the small size, right? Much smaller than main memory. That means some of the information I bring from main memory to cache, if the information is already in the cache, I have to replace it. How and where? I mean, those are the questions. Ideally, cache, we want to have it any memory, any information. If all of those in the cache, that's the perfect. Some cache terminology in our book. Block size, that's the important. Block size is a byte of data brought into cache at once. The key word is at once. And let's say some other architecture. We have a cache size as 1 word. 1 word, there's no universal definition of 1 word. 1 byte, we have a universal definition of a 1 byte. How many bits of 1 byte? 8 bits. Regardless of what architecture type that we have, this is the universal definition. Always 1 byte is 8 bits. However, 1 word, there is no universal definition. 1 word and the different architecture, they have a different number of bits. So let's say we have 64 bits of main memory. When we say block of memory bring into the cache, always this is the block, whole block. I don't care total number of bits. When we say bring the main memory to the cache, we always bring as a whole block. This is the whole block. And if this is 64 and this is the one word, and we're gonna define in our class, one word is gonna be 4 bytes. That's our definition. Okay, for this class, we said for ARM architecture in our class also, one word is the 4 byte, which is 32-bit. If I need to bring one block from main memory to cache, I need to use 2 blocks of cache. So that's the definition of the block. And then we'll look at the set associative and then total number of set over index. I mean, all of this, we'll talk more about that later. And we're gonna talk about direct map cache, n-way set associative. We'll look at one-way set associative, two-way set associative, three-way set associative, and then we're gonna also look at fully associative caches. So let's do this. I think we have to come back next time.